Hello everyone, today I'm solving Leetcode question 72 at a distance using the dynamic programming. So I have uploaded a previous video solving this problem using recursive solution with memoization, the top-down approach. And then you can also see from my screen that the solution is already listed here. So if you want to see the details of this solution, please feel free to check my other video on this at a distance. Today, this video is focusing on solving it using dynamic programming approach, the bottom-up approach. So let's revisit the problem statement for added distance. Given two strings word1 and word2, return the minimum number of operations required to convert word1 to word2. You have the following three operations permitted on a word. You can insert a character, you can delete a character, you can replace a character. So in example 1, in order to convert word 1 into word 2, so you need at least three operations. First, you replace H with R, and then you remove the R in the middle to convert it to rows, and then you remove the ending E to convert it to ROS. So three number of operations needed. So to solve it using the recursive approach, let's revisit how we solve it using the recursive approach. So we use memoization, basically specifying a cache. It's a Python dictionary. We use it to keep track of the values we have already calculated before. And then we define a helper function and then taking input ij. So it means, okay, this helper function return the added distance between word I starting at word 1 starting at position I and word 2 starting at position j. So that's kind of how we break down the entire problem into the subproblem. In the end, what we need to call is just to call helper 00. That means, okay, you will return the added distance between word 1 and word 2. I mean, word 1 starting from position 0 and word 2 starting from position 0. They're essentially just word 1 and word 2. So in the subproblem, like define helper ij, we first consider the base case. Let's say either one run out of index, which means, okay, we have, in this case, I greater than equal to the length of word 1, which means we have already considered all the characters in the word 1, but there's still characters left in the word 2 that need to be matched or converted. So in that case, we insert this number of characters into the word 1 appended to the end so that we can convert that to word 2. And then the second case is, let's say we run out of index in word 2. So in that case, we return the length of word 1 minus I, which means, okay, we still have some remaining characters left in word 1. In that case, we need to delete those characters. So those are our base cases. And then we run our recursion. Let's say first start with, say, ij, if they are in cache or not. If they are in cache, they have already been calculated before, so there is no need to repeat it calculating the same value over and over again. So if it's not in cache, we need to calculate them. So we first by comparing the character at index I and j. So if the characters are equal to each other, so they are the same characters, then we do not need to perform any operations for this position. So cache ij is just equal to helper I plus 1, j plus 1. So which means we do not need to perform any operation at the current position. So we move on to the next position for both word 1 and word 2. Else, if they are not equal, we need to perform one of the three operations. So insert. Take this example. When we're trying to insert something, here after the insertion, we match the character at at index j in word 2. So in that case, we need to move on to the next position, j plus 1, and then trying to match it with the current character at index I. So that's 1 plus helper I, j plus 1. Or we can do the deletion. In the deletion is 1 plus helper I plus 1j. So in that case, after we delete this character, so for the word 1, we should move on to the next character. So that's a character at index I plus 1. But for word 2, the character at index j hasn't been matched or converted to yet. So that's why we remain at the index j. If we replace, after we replace the characters, we just move on to the next index for both word 1 and word 2. So that's kind of the three different operation scenarios. So in that case, we just combine them and return the minimum one. So basically, consider all the three different possible options: insertion, deletion, and replacement, and then return the one with the minimum number of add operations. And then in the end, we just return cache IHA. So this is our solution using recursive approach we just reviewed. So now I'm solving it using dynamic programming approach. So the reason why I start with the recursive approach because this top-down approach is very intuitive to come up with. So for the dynamic programming approach, sometimes it may not be super intuitive to come up with at the very beginning. But if, say, after you get the recursive approach, then it's not super hard to convert that into a dynamic programming bottom-up approach. So this is bottom-up approach. So we first need to define a matrix. So let's first get the length for word 1 and word 2. So we start as dp. So what does dpij mean? So that means the added distance between word 1 I and word 2 j. So here in this dynamic programming approach, we're using the bottom-up approach. So in that case, that's why we start considering we start with a matrix dp, and then dpij represent the added distance between word 1 up to the position before index I, which means that's word 1, the character starting from index 0 to the index I minus 1. And then also word 2, starting from the index 0 to index j minus 1. So in that case, it's 1 m plus 1 for in range m plus 1. So in the end, what do we need to return? In the end, return dp mn. That is the added distance between the word 1m and word 2n. Okay, after having this dp matrix, so let's consider the base case. So base case for I in range m plus 1 dpi 0 equals I. For j in range n plus 1 dp 0 j equals j. So what does the base case mean? Base case means, let's say, in case, let's say, either of the word 1 or word 2 is an empty string. In that case, when we're trying to convert that to the convert word 1 into word 2, so the operation is pretty intuitive. So let's say right now word 2 is an empty string, and then my word 1 we consider at position up until I. In that case, we need to convert that to word 2, the empty string. In that case, the operation is just the delete those. So this is our base case. Then let's fill the dp table. So for I in range I 1 m plus 1, for j in range 1 m plus 1, we comparing the character at position I minus 1, and word 2, j minus 1. So why we are comparing at n minus 1 and j minus 1, re remember that what the meaning of dpij is added distance between the word 1 up until the position before index I. So the last character is word 1, I minus 1. And then for word 2, the last character in this comparison is j minus 1. And then this is something not included in the dpi minus 1, j minus 1 calculation. I mean, if those characters are the same, so this one equals just dpi minus 1, j minus 1, which means no operation or no item needed. Else, dpi j equals 1 plus minimum dpi minus 1 j dpi j minus 1 dpi minus 1 j minus 1. So if the characters are not equal to each other, then we need to perform one of the following 3 operations: insert, delete, and replacement. And then we just pick the minimum one from it. In the end, we just return dpm n. So this is our dynamic programming approach from the bottom up. Let's try run the code. Okay, so when I run the dynamic programming, the recursive solution with memoization, the top-down approach, actually the runtime was a little bit faster than the dynamic programming bottom-up approach. But usually, I mean, it's more, usually it's a little bit faster for the iterative approach. So this is our solution. So if you want to check the details for this recursive solution, how I came up with it, please feel free to check my other video in this playlist, the added distance with recursive solution with memoization. Thank you.